Hello everyone! This lesson will cover a type of block cipher design called Feistel scheme. In this lesson, you will learn about the structure and the building blocks of such ciphers, write a Feistel cipher yourself, encrypt and decrypt with it, and learn its advantages compared to substitution permutation networks. A Feistel cipher, also known as Feistel network, Feistel scheme, is another type of underlying design of block ciphers, named after Horst Feistel, the head of the team of pioneer cryptographers at IBM. It is the construction of data encryption standard, DES, and other block ciphers, such as the former Soviet and Russian GOST-89 and the more recent Blowfish and Twofish ciphers. In a Feistel cipher, encryption and decryption consist of iteratively running a function called the round function on the plaintext block a fixed number of times to produce an output block. A Feistel network uses a round function, denoted as f on the diagram, which takes two inputs, a data block and a round key, and returns one of the same size as the data block. Each round, a round key is derived from the initial secret key and added to the ciphertext. Usually the round keys are added by XOR in Feistel networks. Each round, the round function is run on the half of the data to be encrypted, and its output is XORed with the other half of the data. This is repeated a fixed number of times, for example 16 for DES, and the final output is the encrypted data. Decryption is done simply by applying the round keys in the reversed order. The whole scheme stays the same. In this example, you will be constructing a 16-round Feistel cipher with a 64-bit block size and key size based on a simplified version of DES. The algorithm will consist of plaintext partition and padding, key scheduling function, and round function. These operations will be combined into encryption and decryption transformations, and together with the key generation function will form a cryptosystem. Transformations in the Feistel ciphers usually operate on individual bits rather than the bytes of the key and the data, but binary data is more difficult for a human to read, so to conveniently convert between the two representations, let's define a pair of helper functions. A function bytes to bits will take a list of byte values and convert it to a list of corresponding bit values. And the bits to bytes function will take a list of bit values and convert it to a list of corresponding byte values to simplify human perception of it. For message encoding and padding, you can reuse the same approach as in the SP network ciphers example and the message encode and message decode functions defined in the previous lesson. String message is encoded as byte values of characters in it and padded. Same as in the previous lesson, even if the input message splits into blocks evenly, that is in the case that pad value variable is 0, the input is padded with a whole new block. So the decoder later knows that the last bytes are always padding bytes and can remove them correctly. Let's test it on a plaintext of different lengths using the correct block size for DES, that is 8 bytes. Here the first, the last and the only block is 4 bytes shorter than the required 8, so it is padded with a 4-byte value 4 times. And here the last block is 3 bytes shorter than required 8, so it is padded by 3-byte value 3 times. After decryption, the padding has to be removed to get back the plaintext. The last byte is always a padding byte since we always pad the input, even if it splits into blocks evenly, so the decoder takes the value of this last byte and drops the needed amount of padding from the end. Let's try decoding some of the padded bytes. Here the decoder function successfully removes the 4 last bytes, and here the 3 last bytes. The key generation step is also very similar to that of the previous lesson, with the only difference being the required key size. The initial secret key for the cipher should be 8 bytes long, and you can simply generate a list of 8 random byte values with random integer. In practice, special cryptographically secure random number generators are used. The actual key scheduling algorithm of DAS is quite sophisticated. It starts with a 56-bit key, involves permutation, removal, expansion, and shifting of the bytes of the key. Since every round function f works only with the half of the bytes of the data, left or right, only half of the bytes of the round key are needed at a time. For this example, you will use a simplified version of key schedule based on that of DAS. The algorithm will permute bits of the key each round and use the left half to encrypt the left half of the data and the right half to encrypt the right half of the data. First, define a permutation on all 64 bits of the key. And try it on a randomly generated key converted to a bit array representation. Notice that it permutes the 64 individual bits of the key, not just the 8-byte values we have generated initially. You can see that after a bit permutation, the byte values are completely different than those of the initial key. This would not have happened if you only permuted the bytes of the key directly. Thus, the bit permutation of the key each round is creating a more complicated relationship between round keys. The key schedule of DAS also circularly shifts the bits of the key to the left by 1 or 2 places every round. For simplicity in our example, let's just shift them 2 places every round. Finally, compose the permutation and the bit shifting into a key scheduling function. The key scheduling function will apply the permutation and shift the bits of the key for each of the 16 rounds required. This version of the function takes the key in bits representation, and following is the same function but defined for byte representation of the key with the help of the functions bits to bytes and bytes to bits that we have defined earlier. For example, define a key as the list of bytes in a range from 1 to 8 and check the order the keys will be used in a schedule. You can see that since you were applying a permutation to the bits, the keys now all have different byte values and look completely unrelated to each other, even though they were all derived from the same initial key. For decryption, the round keys will be the same, but used in the reverse order. The Feistel network round function also employs substitution and permutation operations to produce the ciphertext. In DAS, a 32-bit half of the input block is expanded to 48 bits. By copying certain bits, 8 different DAS boxes take 6 bits each and substitute another 4 bits for them, and finally a permutation is applied to all 32 bits. For simplicity in this example, you will omit the expansion and just process the 32 sub-block as it is. In our example, the S boxes will take 4 bits of the input and substitute a different 4 bits for them. Possible values that can be expressed in 4 bits are from 0 to 2 to the power of 4 minus 1. For a faster substitution, let's define the S box as a lookup table. This table will have lists of bits and the lists of bits they have to be substituted for. The substitution layer of the round function will consist of 8 such lookup tables, not a single one like we had in the substitution permutation network example last lesson. And the P box is simply a permutation of 32 bits. For encryption, each round function is a sequence of round key addition, substitution, and permutation applied to a half block of the data. First, the round function takes the left and the right halves of the input block, adds the round key to the right subblock, splits it into 8 parts, each 4-bit long, performs substitution on each part with the 8 respective S boxes, glues the parts back together, and then permutes the bits, and finally XORs with the left subblock of the input. For decryption, the round transformation is identical. The decryption transformation does not need to be inverted. It is identical to encryption, and only the round keys have to be supplied in reversed order with respect to that used during encryption. Test that our functions defined make a round trip. First, generate a random round key and express it in bits. To avoid splitting and joining after each round, our round function treats the input block as it is already split into two halves. So let's split it into two halves. Encryption and subsequent decryption on the same key should give back the same input block we defined. And it does. Finally, combine all of the steps above into an encryption transformation. Notice that the halves of the blocks are swapped, that is, reversed, after each round, except for the last one. The encryption transformation takes a string plaintext with an 8-byte list key, encrypts it into 16 rounds, and outputs a string ciphertext. First, it encodes the padded message into its bit representation, then splits every block into two halves, schedules the 16 round keys as defined earlier, applies encryption round function 16 times. The reverse function here flips the two halves of the block after each round. In the end, the subblocks are joined back together and the bits are decoded back into its string representation. Let's see if it works. Define a random key and try to encrypt the message. Well, this looks quite encrypted to me. The decryption transformation takes a string ciphertext with an 8-byte list key, decrypts it into 16 rounds, and outputs back a string plaintext. First, it encodes the ciphertext message into its bit representation and splits every block into two halves. Then it schedules the 16 round keys in reversed order, applies the decryption round function, which is identical to encryption round function, 16 times. The reverse function here flips the two halves of the block after each round. In the end, the subblocks are joined back together, and the bits are decoded back into a string. Let's try encrypting and decrypting some messages. Well, our test message works, but you can try a few more yourselves. An important advantage of Feistel ciphers compared to other cipher designs such as SP networks is that the entire network is guaranteed to be invertible. That is, encrypted data can always be decrypted, even if the round function itself is not invertible. The round function can be made arbitrarily complicated since it does not need to be designed to be invertible. Furthermore, the encryption and decryption operations are often identical, requiring only a reverser of round keys order. Therefore, Feistel ciphers require significantly less circuitry for implementation, making them the top choice for devices of restricted computational resource, such as integrated circuit cards or smart cards. This lesson concludes the overview of symmetric cryptography, and the next lessons will go on to public key cryptography.